everyone, this is PrachiGupta. Today we are going through PyTorch Tensors collab from zero to hero. It's a comprehensive guide to tensor operations for deep learning. What you will learn in this collab: what are tensors, how do we create tensors, the attribute of tensors, indexing, slicing, basic operations, reshaping tensors, linear algebra, Einstein summation, common DL operations, and some practical problems. So let's move ahead. First, we will import some libraries that are required for PyTorch. We need to install Torch. We need to install NumPy. We are installing Matplotlib for future uses. Now we to check to use all the functions of PyTorch. We'll use it using torch dot. So if you want to see the version of the torch, we will do torch dot version. To check if CUDA is available, we will do torch.CUDA available, and if it's available, we will see which device. So we'll do torch.CUDA.device name like this. I'll run it, and it says PyTorch version 2.9.0 and CUDA available is false. So let's move ahead. What is a tensor? So it's a universal data container. A tensor is a generalization of a vector matrices to potentially higher dimensions. So it can be one dimensional, two dimension, three dimension, zero dimension, or a higher dimension number. So see, these are some examples: one, two, three dimension vectors. How zero dimension looks, how one dimension looks, how 2D, how 3D looks. So let's create tensors of different dimensions. How we will create it? Tensor torch.tensor 42, and value is equals to scalar, shape is shape, and then the dimensions. So it will, the shape and dimension use cases are same like it's in NumPy we discussed earlier. So I'll just run it, and zero dimension tensor is created with value 42, and the shape is blank. So this is how a zero dimension tensor is created. Now let's create a 1D tensor. So to define a tensor, again we will use torch.tensor, and inside that we will provide a list that is a 1D list, and then it will create that list. We will print the value, vector, directions, shape, the dimensions, and the element, number of element in that particular tensor. So we have stored the tensor in a vector. So we'll do vector dot shape, vector dot end dimension like that. So these are the output. We'll again create a 2D tensor. So for that we will give a 2D nested list, and then we will store that tensor in matrix, and then matrix we will shape, will print the shape, the dimension, and the number of element. So I'll just run it. We can see the dimension is 2, number of element is 9, the shape is 3 cross 3. Moving towards a 3D tensor, we will do a triple listed nested list, and then again we will print the shape, dimensions, and the number of element. So this is how it's printed. Now why tensors in deep learning? Tensors offers many way to create tensors. So before that, why do we need tensors in deep learning? So tensors are useful in various places. In feature vector we will use tensors. We'll use batch vectors, grayscale image, color image, batches of image sequencing. Everywhere tensors will be used, and these are the types shapes of the tensor that will be used, and these are some examples. So let's move ahead to the code. First we will create tensors. We can create tensors from different types, like we can create from a Python list, we can create from a nested list, we can create with floating point numbers. So we just have to do tensor torch and then tensor dot torch, and inside the list we have to pass the element. So here we have passed the Python list, we have passed the nested list, and here we have passed a floating point numbers list. So I'll just run this to see the tensors that are created and the type of those tensors. So for the float one that we created, we can see the torch type is float, and torch type isn't here, and this is how it's created. So let's move ahead. So this is how we create the tensors from Python list. Now we will see how we can create tensors from NumPy array. So suppose we have this np.array, this NumPy array. Uh, what we will do is torch dot from NumPy, and then we will give the NumPy array. So from NumPy is a function that converts NumPy to tensor. So this is how we create tensors from a NumPy array, and we will print it, the tensor, the NumPy, and then after modifying we can see what comes. Let me run it. See, so this is how the NumPy array was. We created the same tensor, and once we changed the NumPy array, we did 0 comma 0 as 99 999. So after modifying a NumPy array, we can see what changes we did in the NumPy. The tensor's value also changed. So basically, they shares the memory. So if we do one change on the NumPy, the same change would reflect on the tensor as well, because they are sharing the same memory. Now let's move forward. To avoid memory sharing, what we can do clone, tensor.clone, or we can do we can do torch.tensor. So this is a NumPy array. What we are doing, torch.tensor NumPy, it creates a copy instead of sharing the memory. So now when we change our NumPy, it won't modify our tensor. So if I run it, now see, the NumPy array is modified but tensor is unchanged. Let's move forward. Special initialization functions. So in the same way we saw in the NumPy, we have zeros function in tensor as well, we have ones function in tensor as well, we have a full function in tensor, and we have a I function in tensor. So let's run all of this one by one. So all we have to do is torch.zeros. So pytorch.0. So it will create a tensor of 0 0. Similarly, we will do torch.1, so it will create a tensor of all ones of that given size. Now we will move next. We'll see. I'll just run it. Okay. Now we'll move to the full. So what it will create? It will create a tensor of size 2 comma 3 with all value as 3.14. So if you see, I'll just run this, and we can see this tensor is created with this size and this value. So this is how full works. Now let's move to I. So it's again the same identity matrix. We just have to give the size, and it will create a identity matrix, identity tensor from torch.I. So this is how it works. Now let's see how arrange works. So we have given torch.arrange 0 comma 10 to 2. It's basically start, the end, and the step. End is the exclusive. So what it will do, it will arrange, it will start from 0 to 10, and it will take 2 steps at a time. So if you see the output here, I'll just run it. See, from 0 to 2, 0 to 2, 2 to 4, 4 to 6, 6 to 8 till 10. So this is how arrange works. And for line space, we give the starting and ending steps, and we give the number of points. So basically it gives 5 equidistant points between the given starting and end number. So this is how it creates this points. Let's move ahead. Now we will see random tensors, how to generate random tensors. So what we will do, we will set the seed for reproducibility, and we'll move ahead. So uniform torch dot random 3 comma 3. So it will create a random tensor of 3 comma 3 size. If I run this, let's see. It has created a random tensor of size 3 comma 3 with all the values ranging between 0 to 1. let's move ahead now. Again we are creating one random tensor and I'll just print it. Again one random tensor got created with all the values between 0 to 1. If we move forward, this is again we are creating a random int. So we have here given like lower limit, higher limit, and the size of the random tensor that we want to create. So it will create a random tensor of 3,3 size with all the values ranging between 0 to 10. So this is how it works, random int. Now moving ahead, we will visualize how the data is created. So we'll create three visual plots. One is for the random tensor creating uniform samples. One is the random tensor by creating samples of normal distribution, and one we will create with simple integers with a normal random function. Let's see how this works. So this is how torch.random will give. Normally torch.random will give you the values like this. If you do torch.rand n, so n here will mean normal distribution, it will give you data like this. And if you give torch.random integer, random int, it will give you data distributed like this, almost on an equal level. So moving forward, uh, let's see how to create a reference tensors. So we have this tensor and we have the data type as torch.float. So we have this reference tensor created, and we can pass this reference tensor, like we can create tensors with the help of same shape and data type. So let me just play it. Okay, so we have created a reference tensor. This gives the shape and the size and the type of the data. So I will create a zeros tensor with the same reference, a ones tensor. So it will be of same shape and same type. Only the values will be varying. Other things will be same. That's the main difference. And this is how the reference works. Now we will see tensor attributes like shape, data type, device. So again it's similar to what we saw in the numpy. The only thing is how to use it. So similarly we will define a random tensor and then we will print the shape of it, we'll print the size of it. To access the individual dimensions, we will give the dimension number here, shape call in the square brackets 1 2, and then if we want to print the number of dimensions, so we will give n dimensions, and if we want to print the number of element, we will give the n element. So we can see the tensor size is 2 comma 3 comma 4, the dimension of 0 is 2, dimension of 1 is 3, dimension of 2 is 4, and then number of elements, number of dimensions, and the total elements. Now let's move toward the data type. So there are all these kinds of data types in tensors: float 32, float 64, float 16, b float 16, int 64, int 32, and the boolean. So let's move ahead and let's see how do we use them. So we have one integer tensor, we have one float tensor, and we will print the data type of those. We will see if we can explicitly define the tensors while creating the tensor, like we can explicitly define the data type. And let's print the tensors we created right now and see the data types. I'll just run it. So we created one integer tensor here, we created one float tensor here, then we explicitly defined this tensor as float. See, we gave normal numbers, it came in the float form, and it came in the float 16 form, and this is a boolean. So this is how we explicitly define. Let's see type conversion and casting in the tensor. So here what we are doing, we are creating an original tensor, then we are converting original the tensor name 2 torch dot the data type that we want to convert. Method 1 is using dot 2 function. Method 2 is using dot the data type name. So we can also give original dot float, original dot double. It is same as 2 in bracket double or 2 in bracket float, like that. So I'll just run it and see, it is the original tensor. It converted it to float, it converted it to float 64, all the different types of conversion. So this is how it works. Now PyTorch can run on CPU or GPU. GPU operations are much faster for large tensors. So CPU is good for small tensors debugging, but GPU is essential for training the neural network. So to check the device, we'll see CPU tensors torch.tensor123, torch.device. So if we will check if CUDA is available or not, and then we will set the random, will initiate one specific device. We'll create a tensor on a specific device. So I'll just run it. So we have default devices CPU tensor, and then if CUDA is available we will give the CUDA name, otherwise we will give CPU. So CUDA is not available, so we have given CPU here, and then we will create a tensor on CPU. This is how what we are seeing. Now moving forward to the next, we will be moving tensors between two devices. So suppose a tensor, we have CPU tensor created, random and random normal distribution tensor, and then torch CUDA is available. If CUDA is available, then we will CPU tensor to, so we have this CPU tensor, we will change it to CUDA, and then it will change it to the CUDA, and if and it will then back CPU to GPU tensor. Let me just switch to GPU, and then we will see how it works. So earlier CUDA was not available, so it was learning only on CPU, and this is fine for learning. So now I have connected my runtime to T4 GPU. Let me try running it. Okay, got it. So as I have changed the the runtime, so I have to run everything from starting to get the installations done. So importing the library files, let's go to the file again, where the cell again that we were running. Okay, yeah, this was the code. Okay, yep. So this is the cell where we got error. I'll just run it again, and yeah, we are done. So GPU tensor device CUDA, we have CUDA, and then back to CPU again. So to change CPU to GPU, we do CPU to dot tensor the CUDA, and then if we want to move back to CPU, GPU tensor dot to CPU. So this is how we can change from CPU to GPU. We can move tensor between the devices. Okay, now let's move towards indexing and slicing. A specific element or a row or a column or a sub element we want, we can get it through slicing, indexing, and this is similar to what we have seen in the NumPy. Let's move ahead. So we have created one tensor, we have printed the tensor here, and then we have created a tensor vector, and then we have printed a vector here. If we want to access a single element, we can access by square brackets and giving the index number, and if we want a particular range, we can give the range. The last element is exclusive, the first element is inclusive. That thing we have to keep in the mind. Let me just run it. Okay, so it says that step must be greater than 0. Okay, so we are getting this error for minus 1. So in tensors, step can't be negative. So what we have to do, this is what we used to do in the numpy. To reverse the tensor, we have to use dot flip function and we have to run it. So see, our tensor was 10 to 50, it got flipped. So this is how it works. Let's move forward to indexing. We have already seen 2D indexing in NumPy, column 0 to 1, rows 0 to 1. The same indexing is used here. To access a particular element, we can use the number of, like, the row address and the column address. So if I run it, it says 0 0, so it will be 0th row, 0th column, that is 1. 1 2, so it will be first row and second column, it will be 6. So 1 6 9, like that. Let's move forward to print, to select row and column. If you want to select a particular row, if you want to select a particular column, how do we do it? This shows that. And then if you want to select a submatrix, then we have to give a proper row definition and the column definition by slicing. So this is how it works. Now let's move towards the advanced indexing, that is fancy indexing. So here we have defined one tensor. We have defined, select the rows, what rows we want to select in a tensor, and then we will pass it. So we will define row indexes, we will define column indexes, and then we will pass them into the main tensor, and it will print that particular indices and the column. It's basically similar to this thing. The only thing is we have stored this and this part in rows and column indexes, that's it. So I'll just run it and it's executing. Now boolean indexing is again same as masking. Boolean indexing, masking is same what we saw in the numpy. We can create a boolean mask. Suppose we created a mask for t is greater than 0 and we put it into the tensor. So it will, what it will do, whatever value is greater than 0 it will give true, otherwise it will give false. Similarly, we can use it for filtering. If element is greater than 2 or something, then only print it or something like that. Whatever masking we want to do, we can do using it. Let's move forward. We have to do basic of tensor operations. So the same way we used to do in the numpy, we can do addition, division, multiplication, subtraction, all the basic operations on two tensors. We can add to all the adjacent elements will be added, multiplied, divide. So 1 plus 4 5, 2 plus 5 7, like that all the operation works. Let's move forward. We have function evaluation. So we have also predefined function add, subtract, multiplication, divide, that will automatically do this the same job. So we have defined already a and b. We can do add, a comma b, subtract, and all those operations. So it can be done like this as well. So this is how we have seen we do the operations. Now some other common operations are square root, exponential, logarithmic. We can call all these functions by torch.sqrt, torch.log, torch.log10, torch.sine, torch.cosine, and then torch.floor for the float variables, torch.cell for the float variables, and torch.round for the float variables. So this is how it actually works, and if I'll run it, it's doing all the thing. We have just passed simply a tensor, and then we have applied all this operations on this particular tensor. We have passed the tensor in the brackets. So this is how it actually works. Now aggregation functions, we can do the aggregation functions as well, like sum, min, standard deviation, variation, minimum, maximum, product of all elements. All these are predefined global aggregation things that we can do on our tensor. So we just have to do tensor name dot and the function. Let's move forward. Next is aggregation along the specific dimension. So if we want to reduce, aggregate down any column or aggregate across any rows, we can do the same using this aggregation by passing this element. So in the sum we will pass the dimensionality as 0, so it will aggregate down the rows column, and then if we pass it as 1, so it will aggregate across the rows. So for columns we are going like to reduce the rows we will pass 0, to reduce the columns we'll pass 1. So I'll just run it, and we can see dimensionality 0, so it removes the 0th row. If we give dimensionality 1, then it removed the first column, and we got 6 and 15. So this is how it works. Let's move forward. So I just train it. So we can see from this it removed the first, it just added like basically it aggregated the rows into one row. So it removed first row, it added 1 plus 5 plus 6 plus 9, and then we did dimensionality, so it gives 6 and 5 50. Okay, so like 3 plus 2 plus 1 got 6, and 6 plus 5 plus 4 got 15 into a single dimensional. So this is how dimensionality reduction works. Now let's see finding indexes of minimum and maximum. How can we find it? So we can use aggregate max function to get it, and we can use aggregate minimum to get it. So if I'll run it, we can see there are 3 samples, 3 classes, and this is our vector, and we have printed our vector, and predicted classes max along the dimension 1 is 0 1 2 1 0 and 2, and argument min is 0 1 and 2. So this is how it works actually. Let's move towards broadcasting. So again, broadcasting allows operations between tensors of different shape. PyTorch automatically expands a smaller tensor to match longer ones. The same thing we saw in the NumPy. And then it again follows the same rule. It aligns shapes from right. Dimensionalities are compatible only if they are equal or one of them is 1. Missing dimensions are treated as 1. The same we used to do in the NumPy. Let's move toward the broadcasting example. So we have a scalar plus tensor, we have a vector plus matrix, two types of. So we have this tensor, we will add 10 to this tensor. We have this tensor, we will add this vector to the tensor. I'll just run it to see the outputs. So 10 plus, we'll do 10. So it will be 11, 12, 13. We will add this to this tensor. It will be 11, 22 and 14, 25 like that. So I'll just run it and it works. Now we can do column wise broadcasting as well. For that what we have to do, I'll just run it. So we have this tensor, we have this again a tensor, and we will print our first and second column, and then we will add them. So it will add 100 to first rows and then 200 to the second row like that. So this is how it works. I'll just run it. Now for in place operations, operation ending with underscore, modify tensors in place and save memory, but can be careful for the autograde. We have to check it. So let's see. We have torch.tensor 1 2 3, original is t, and then we have to do t plus 10. We have to add underscore 10, so it will do at the place only, and multiply, subtraction, divide. So all these functions we are doing on this at the same place only. So if I run it, after adding 10, unchanged tensor is this, but if we add underscore 10, operations will be on in place, and the will be changed, the tensor will be changed. Now moving towards the reshaping tensors. So reshaping tensors is also one of the essential for connecting different layers in neural network. We can, when we will need the reshaping for flattening images, for adding batch dimension in a single sample, rearranging dimensions for convolution, combine or split batch sequence dimension. So this is the scenarios where we will need it. Now we have view and reshape. So if we want, if we have this torch arrange 12, so it will create a tensor of 0 to 12 and reshape 2D. So we have created a view, and then we will just let me run it. So what we have done here is we have created this tensor, we have created a view of this tensor out of this tensor, we have created one more view out of this tensor, and we have created one more view. So basically we have rearranged our tensor in these three different views, in these three different dimensionalities, or whatever we can see. So this is how it works, and then again we are creating different views, and then uh, we have to, if we have to reshape, so basically when we create the view, it will not change our main tensor, but if we are rearranging, it will, we are doing reshape, then it will change the tensor. So reshape works even if tensor is not contiguous, and generally prefer reshape because it's more flexible. So I'll just run it, and here is the reshape. So now we will see the flatten. It is essential for connecting convolution layers for fully connected layers. So we have we have this tensor of random normalization tensor we have created of two batch, three channels, four height and four width. So this is the shape. We can see the shape of the image from starting table that we mentioned. Hmm. Yeah. So for image we had channel, height and width, and if there is a batch of image, then we have the batch, channel, height, width, all these shapes. So I'll just move back to the part we were looking at. Yeah. So flatten, we created this batch, channel, height, and then we will do a flatten, and we will see the flat shape. Uh, and then we will see how it is impacting and view the shape. So I'll just run it. So we can see image patch shape torch dot size. After flattening, the size has been changed. All this different dimensionality has came into a 1D tensor vector, and then if we reduce by giving the dimensionality, then it is modified accordingly. So this is how the flatten function works. For squeeze and unsqueeze, uh, we can add a dimension of size 1, or we can add a dimension of size 1, or we can to add a dimension we will use unsqueeze, and to remove a dimension of size 1 we will do squeeze. So this is a tensor, and then we will see first the shape, and after that we are doing the unsqueeze operation, and then we will print the tensor. Let's see the output to understand it more better. So this is the original shape, and once we unsqueeze the shape, you can see it changed from 1 to 3. And this is one more tensor we have, and if we unsqueeze it to 1, the shape of the tensor changes to this. So this is how it affects the tensor, and let's see the squeeze operation now. So this is a random normal distribution tensor that we have created, and we will apply the squeeze operation on it, and let's run it and see how it works. Okay, so this is the normal tensor. When we squeezed it normally, it automatically squeezed and reduced these two columns. But when we passed squeeze 0, it squeezed from zeroth row, zeroth column. And when we pass squeeze 2, you can see the second column got squeezed. So this is how it works. Now we'll see transport and transpose and permute in the tensor. Transpose is basically swap the two dimensions, and permute is rearrange all the dimensions in any order. So there is a predefined function that we can use for creating the transpose, that is t dot transpose. And for permute also we have a predefined function called permute. So we have to give the batch of like the tensor name dot transport, and then we have to give the shape, like what shape we want to transpose it. So I'll just run this code. So we can see this was our original tensor, and then we have transposed it to this new tensor. So let's this was our tensor 1 2 3 4 and 4 5 6. After transpose it became 1 4 2 5 3 6. So let's move towards the cat and stack. So cat is basically the concatenate along the existing dimension, and stack is like adding a new dimension. So when we combine two tensors, so we can do two things: either concatenate the existing tensor to the uh, like concatenate it to the existing tensor, or else we can stack this new tensor to the new dimension. So these are the two ways we can combine the tensors. So let's see the code. This is the first tensor, this is the second tensor, and then we are printing it, and then we are doing torch dot cat and passing the two tensors. And similarly we are doing torch dot cat and passing the two tensors, and we'll see the shape of both once we'll do the cat. Let me just run it. So see, this is our 1 2 3 4 and 5 6 7 8. So when we do cat ab, so the b goes and then it extends the vector a. If we do dimensionality 1, if we do dimensionality 0, basically it adds on as new rows, and if we do dimensionality 1, it adds on as columns. Now let's see how stack works. We have these three tensors, we have given torch dot stack abc, and then we will just run torch dot stack abc with dimensionality 0. So again here dimensionality 0 means the rows, it will extend in the rows. So let me show you the output. I'll just run it. So you can see stack abc 1 2 3 4 5 6 7 8 9, and the size is this. And if we do with dimensionality 1, so it becomes 147 instead of 123. It is coming like this, 147. So this is how it works. Now let's move towards the next part, that is linear operation algebra operations, which is matrix multiplication, dot product, norms, matrix decomposition. So this at the rate we have seen in the numpy also, it's for multiplication. So similarly matrix multiplication is done here in the tensors as well. We use this we can use it three ways: by this at the rate symbol, or by torch dot mm, or by torch dot matmul. So these are the three ways we can do the multiplication in tensor. So the results are same for all the three forms. Next, moving to the next part, that is batch metric multiplication. So we can do it in the batches as well. We have defined a batch of 32 matrices. We will do torch dot matrix multiplication. We will pass the batches one by one, and we will print the shapes as well. So if I run it, we can see batch multiplication of this torch, and then with this is the output, and these are the sizes. So as we have seen in neural network, there is a formula y is equals to xw plus p, and there xw is the matrix multiplication and where it is mostly required, and b is the broadcasting, the bias that we add to the matrices. So the same thing we are performing here. We are defining x as a random torch dot random normally distributed tensor, and then we are defining again a w as normally distributed random tensor, and b is the bias vector. So this is our weight matrix, this is our feature vector, and this is our bias. So I'll just run it, and we can see the input sizes of all this. And this is what exactly neural network do, linear neural network. Now we'll see the dot products and inner products. So let's see. I'll just So we can see the dot product and the multiplication are the same, as we have already seen in the numpys. Both are functionally same, only the way of defining and doing is different. Let's move to vectors and matrix norms. Norms means the size or the magnitude of the vector. So this is L1 norm, this is L2 norm, and then this is the tensor. Suppose we want to get a L2 norm, then the we'll do torch dot norm of the vector. Here in vector we have 3 comma 4, so L2 will become the square root of 3 square plus 4 square, which is 5. So similarly for L1 norm we will have torch dot norm v, and we will give p equals to 1, so it will perform as L1. And I'll just run it. We can see the output. So this is how it actually works. There are other linear algebra operations which are there, which we can use. We can use trace to get the sum of diagonals. We can use inverse function to inverse the matrix. So I'll just run it and I'll show you the output. This is our initial matrix and this is the inverse matrix. Moving forward to matrix decomposition, we have uh, this eigenvalues. So here we are creating eigenvalues and eigenvectors. So this is how we create. This is B is where we have created a random tensor, and this singular value decomposition is usually used in dimensionality reductions and matrix approximations. So we'll just run it to see the output. So here are the eigenvalues, eigenvectors, and the sizes of the vectors. The next point is Einstein summation, the Swiss Army knife. So Einstein summation is a powerful compact notion for expressing tensor operations. Why do we need to learn it? Its expression is its one line can replace many operations at once. Um, it optimizes the operations and then handle the complex tensor contractions easily. So this is why it's important. What is the format? Torch dot einsum and then subscripts tensor 1 2 all these things, and let's run it. So we have to get sum of all elements. So what we will do, we will define a tensor. We will do torch einsum and then I a, where I goes in and nothing comes out. So I'll just run it and we'll see sum of all, and then a is 1 2 3 4. So what we are doing is here print sum of all I and a2 list and the result. So basically what it do here, we have already done einsum, so it gives the sum and we are printing it here. We are storing it in the result and we are printing it here, so it gives the sum. Now if we want to do element wise operation, we can do with einsum as well. Let's see how einsum can help in matrix transpose. We can define einsum ij to ji. So it basically swap I and j for a. This is how it transposes. For keeping I sum over the j, so basically it gives ij over I over ij, and I'll just run this to see the output. So this is how it actually works. It also helps in extracting the diagonals. So what we can do is when I and I are same, we can get the element. So same index for both the dimensions. So this is how we can get the diagonal from INSUM, and then I'll just run it, and here is the matrix 1 2 3 4 5 6 7 8 9, and the diagonal is 159. So here is the output 159. We can also do two tensor INSUM operations. So we can define two tensors, and then we can pass here, and if the index is same, keep it, and otherwise we can remove it. So this is what we have to do for the multiplication. This is basically dot product of inner product. So for outer product also we can do, for dot product we'll do I comma I, and for the outer product we'll give I comma j goes I and j. So if different indices, we can keep both. I'll just run it, and it gives the output. We can do matrix multiplication also with INSUM, and for this we just have to provide the main thing that we already discussed, like if m cross p and p cross n, then the output will be m cross n. The inner dimensionalities will be not be considered, the outer dimensionalities will be considered. So this is how it does the multiplication. I'll just run it quickly. Here is the output. So here are some more matrix multiplication done by INSUM. This is the basic cheat sheet of INSUM if you want to go through. Like if you want sum of all, what INSUM you have to use. If you want to column sum, row sum, transpose, all this we have already seen above, and this is a cheat sheet that is very helpful. Now, common deep learning operations. We have our activate. We will go through some operations that we will constantly use in neural networks. So one is the activation function. These are the nonlinear functions that give neural networks their power. Without them, stacked linear layers equals to single linear layer. They introduce a non-linearity, and different activations have different properties. We have already seen some activation functions in the NumPy like ReLU, sigmoid, tanh, and leaky ReLU, and the same we will see here in the tensors as well. First we will initiate a line space tensor, and then we will call a ReLU function. We will call a sigmoid function, and we will see the outputs in a graph. I'll just run it. Here is the output graph of all the different functions on that particular tensor. Now we will use softmax for the multi-class classification. It converts raw scores to the probabilities that sums to 1. So basically it converts the tensor into the probabilities which will eventually sum up to 1. So this is how softmax works, and for any particular tensor we can just pass f dot softmax, and we have to pass the tensor in it. So f dot softmax, and we will just simply pass the tensor in it. I'll just quickly run it. Now for loss functions, it measures how wrong our prediction are. So suppose for mean, suppose we have created two tensors, one for prediction, one for target, and we have done f dot MSE loss and predictions. So we are printing the prediction, target, and then in the MSE loss we have to give the predictions and the target, and it will calculate the mean squared error and it will print it. So this is how we use MSE for loss predictions. So f is here the functional library that we have imported. We will do f dot MSE loss, and then we will pass the prediction and the target. And I'll just run it, and it will print the prediction, targets, and the logistic labels, everything. Next is the normalization operations, which is essential for training. So we can do batch normalization by using torch and batch normalization. We can do layer normalization by torch and layer normalization, and then we can also perform this manual normalization, where we can calculate the mean, x dot mean, where we can calculate x dot as standard deviation, and then this is the normalized formula, and we will just print it. So I'll just run it, and we can see this is the original tensor, this is the normalized tensor, and this is the new mean. Now cropping and clipping and dropout. So clipping prevent extreme values. Suppose we have this tensor, and we want to keep the range between -2 to 2. We want to clip out other elements. So what we will do, we will do torch dot clamp, and then we will give minimum, maximum, and the torch, the tensor name. It will clip the tensor vector. Then gradient clipping is basically we have to give the max norm and the negative next norm, and then it is very important for training stability, because it will help in the better clipping. And for dropout, we will randomly zero out the elements. Whatever we will give, we will zero out those elements. So I'll just run it. So this is the original tensor. After clipping from -2 to 2, we just left with this, and this is the after dropout. The last point in this is PyTorch patterns, practical PyTorch patterns. One is weight initialization and autograde basics of, and one we have common code snippet, everyday use, and we have this summary. So we'll just go through it quickly. So we have this some common code snippets that are used in our daily life. So it are like copy paste ready patterns for the everyday use, so you can use it anywhere. This one is for one hot encoding. We can pass the tensor here, and then we can give the number of classes. So we can define, suppose we have defined number of classes 5, and we can pass the tensor, and it will do the one hot encoding for the data. So this is how it works. Then we have second pattern of top k predictions. So again we have defined a tensor of 4 samples and 10 classes, and then we will do the softmax function that we have discussed earlier, and then we will get the top 3 predictions by torch.topk. Will give the probabilities that we got through the softmax, and then we will give the dimensionality. So this top k will get us the top k predictions from the probability tensor that we have created. I'll just run it, and these are the probabilities, and these are the class indexes. Now the third pattern we generally use is the masking. So casual masking can only attend to the past positions. So let's see, this is the casual masking. We have this torch setup done. We have passed the sequence length, and the diagonal, and if it's masked, then we will make it true, otherwise false. And then I'll just simply run it. So here we were masking true or false. We can also mask it with some values, like here we are masking with negative infinity. So I'll just run it. The next pattern is padding sequences, where we can so here we have defined the 3 tensors, and we have done the padding sequences. So if you see the output, it's 1 2 3 0 4 5 0 0. Basically it takes the highest tensor, and then adds the extra variables to make it of same size with the same length, basically it pads it to the same length. Now the last part is gathering specific elements. So if we have a bed size, we have a num class, we will define a uh, tensor with that, and then we will do tensor name dot gather the dimensionalities, and we can use unsqueeze. It will give us this output. So I'll just run it. So this is all for today. This is all things we have done. This is the quick summary we have gone through. um, Creating tensors, tensor property, reshaping operations, deep learning essentials, in magic, and then that's all. Thank you.